especially when combined with deep neural networks. But for this class of algorithms, very little is known from a theoretical perspective, even in very simple problem settings. So that's going to be the focus of this work. So considering a Markov decision process with some state and action space, the goal in reinforcement learning is to find an optimal policy that sort of minimizes the cost to go simultaneously from all states. And sort of what these policy gradient methods do is that they consider this scalar objective L, which just averages this cost to go under some initial distribution. And they search over a parameterized class of policies by doing a stochastic gradient descent. So next slide, please. And one of the main challenge with analyzing policy gradient methods is this objective is almost always non-convex. So even for very, very simple problems like finite state and action MDPs, uh, you can show that the policy gradient objective is non-convex. And this is sort of a fundamental issue because we are minimizing the cost to go, which is fundamentally a multi-period objective. And so our conventional understanding has been that because first order methods asymptotically converge to stationary points, but there is no guarantee on the quality of these stationary points. Next slide. So in this work, we take a step towards that. And we consider an idealized setting where we have access to exact gradients. We assume that the initial distribution rho provides sufficient exploration, so there are no challenges with exploration. And we assume that the policy class contains the optimal policy. And under this, we identify some structural properties which guarantee that the policy gradient objective has no suboptimal stationary points. And under some stricter versions of these properties, we can show that this objective is also gradient dominated. So taken together, we can show asymptotic convergence of policy gradient methods to the optimal policy. And under slightly stronger conditions, we can also show gradient dominance, which implies convergence rates. Next slide. And finally, our results apply to many classical control problems. For example, finite state action MDPs with a class of policies over the simplex, linear quadratic control problems with the class of linear policies, optimal stopping problems with the class of threshold policies. And we also have extensions to finite horizon inventory control problems with the class of non-stationary threshold policies.